Thanks for coming to some of you, the fourth presentation. We also had a look at ways of analyzing optic flow inspired by or taken from insect flight control, insect vision, but with different technology, different approaches on how to do it. And so we have today the presentation of the people from the Institute of Neuroinformatics in Zurich. And give over to Giacomo and Vasco.
So hello everyone, I'm Vasco and he's Giacomo. We are both from the Institute of Neuroinformatics. I'm more as a background an engineer. I've been working a little bit on bio-inspired robotics, and then I moved to doing my PhD on insect flight. So that's where I come from, and Giacomo is more an expert on biomorphic chips. And the project I'm presenting today is the Neuromorphic Computation of Optic flow data and control for landing of autonomous vehicles. So basically the goal was to land, the target is to land in simulation, of course, a vertical takeoff and landing vehicle using an insect-like bio-inspired control strategy and using also a bio-inspired vision sensor which computes the optic flow. To tell you why this is interesting, I can show you this short high-speed movie from the Hegelab lab of a fly landing on a cap. And you can clearly see that if you want to build autonomous flying vehicles, then nature already built some ones which are really good, and we could maybe go and look how they work to get some inspiration and build something which is close to this. The approach we took for this project was first to set up a flexible framework which is allowing us to go from simple to complex without having to change everything. So just add more and more complexity to the system while we are doing the simulations and we know a little more about our system. And in parallel, of course, develop the chip, design it and test it both in simulations, and now that we got the first manufactured ones also in reality. And once we have the framework, we want to integrate the chip in the framework and explore some control strategies for landing using this chip. The framework, summarized, looks a little bit like this. So we have a vehicle which we want to control, a simulation of the environment, an optic flow processing where the chip comes in, and some controller which controls the desired optic flow in this case. And the way it's done is that we basically did it in Simulink in MATLAB, and the environment was simulated using Pango and a combination of Pango and the virtual reality toolbox of MATLAB. So coming to the chip, why this technology that we suggest is interesting and why this is biomorphic also. AVLSI CMOS technology allows building compact, low-power, fast sensors, and also very biomorphic from the point of view that with this kind of technology, it allows very highly parallel computing, as we know that neural circuits do. So with this kind of design, this kind of chips, you can definitely emulate neural circuits. So be as biomorphic as possible. Some drawbacks, there are of course some drawbacks of this technology. One is definitely that we have kind of noisy chips for the moment, and we can't go too high in resolution for the moment. That's what the layout of the chip that has been designed looked like, and we designed a 64 pixels linear chip, linear detector, which is able to extract the speed of the fastest moving edge on the image, or also the average speed of the optic flow on the image, plus it is able to extract the position of the strongest contrast point on the image. Once we designed the chip, we did a simulation of it in Simulink and integrated it all in our framework, and we started doing some simple landing control, which is based on biological observation. This, for example, is very close to what Professor Franceschini Marseille is also doing. It has implemented with his Octave helicopter, which is basically using a single looking down optic flow sensor is able to land safely by keeping the optic flow constant. There are some drawbacks of this design is that if you assume you don't know your speed and height at the beginning, you're not able to land safely, because if you don't have an atmosphere, like in the case of a lunar landing, for example, you're not able to brake in the way you want. So for this reason, we developed a second model, which instead uses two tilted linear sensors. And this way, we are able to perform the same trajectory as the one before, but even in absence of the atmosphere or in the presence of wind, for example, if you have an atmosphere. And this model also allows a purely vertical landing, which the other one doesn't. So starting from these simple models and the linear chip, the outlook, if you want, is going to be to try to put this sensor on some robotic platforms and start playing with them, plus trying to build sensors which are able to sense for the 2D optic flow and not only linear ones. So I'm already coming to the acknowledgements of all the people who worked on this project. Apart from me and my boss, Stephen Fry, who's a biologist working flies, there was Giacomo, of course, Chiara, who designed the chip, Garik, who did the simulations of the chips, Stefan, who worked a little bit on the controller side, and of course our nicely dressed contact at STEC, Tobias.
This picture, we have to talk.
Okay, that's it for the executive part of the talk.